A few advanced features, right? One thing we want to learn is experience, is pointers to functions. Let's save this. Func ptr. Let's see. All right. So I'm gonna declare two functions, f and g, that say return int, and take int and return int, right? Int f, int argument I, and we return I plus 1, and then int g, int I as well, return I plus 2. So I have two functions, and then I would like to create an array of functions, right? We're familiar with this concept because we've done that in Python, right? We know that we can have lambdas and we can put the lambdas in an array if we want to. But let's see how we do it in C. The first difficult aspect of C is that it doesn't allow you to have anonymous functions. Functions always have to be named. So you can't create them on the spot. They cannot be anonymous, and we also don't have lexical scoping, right? So one good thing in Python was that I could refer to a variable that was not inside the scope. All right, so I could have a lambda inside a lambda, and the inner lambda could refer to variables declared in the outside of the lambda. Right, this is not possible in C. But this is not really a very serious limitation because we can always add more arguments to our functions, right? So whatever needs to be in the outer scope, we can just pass it in as an extra argument, and it sort of works. But the interesting thing is what would be the type. So I want to have an array of functions, right? So the type of function is right. So int brackets would be as a type would be the type of a function, right? So it's interesting that now I need to have a pointer, right? So I need to put a star here, okay? And this needs to be an array. So it's going to have the array here as well, right? So let's see how we do the full declaration. So I'm going to say how do we do the declaration? Now that's very interesting. So we're gonna put the array here, and we're gonna say that we want to have two elements, right? And then we don't need this. All right, and we want this to be f and g. So there's quite a bit of magic that we need to absorb now. First of all, let's try to figure out the type of ARR. All right. So when we do this, we have to treat all the types as operators, and we also want to say before we do anything. So we want to treat all the type operators as operators. So this is an operator that contributes to the type. This is another operator that also contributes to the type, and this is another operator that also contributes to the type. Right? These types have precedence, and the rule is that the brackets always bind tighter than the star, because the brackets and the star are on different side of the symbol, right? So if we were to attach brackets, but we and actually we could attach brackets, we should attach them like this, okay? And actually with the brackets, if I remember correctly, it should work, right? So the star is the least powerful in this case. So then if we have the brackets, let's try to read the type of array. So array ARR, right? ARR is an array. This thing tells me that it's an array of two elements, right? And now we're doing the wrong thing. I actually want to put the brackets like this. So it's an array, because of this, it's an array of pointers to functions whose arguments are int and the return type is int. Right? So this is quite weird. Now, these brackets are redundant, but let me just reassure myself, because I haven't done this in a while. Let's see that we can compile this. GCC minus O func pointer. Let's see. Implicit entry start for main XQ, but if the symbol is not found or architecture. It's very strange. Is this compile? Yes. If I remove this. Oh, I think I hadn't saved. I hadn't saved the file. All right. So this actually works. And then these brackets are in fact redundant. Okay. So let's do this again. We always read from inside out. Another weird rule for C, right? So ARR, and then on both sides we have an operator, and brackets always build by type. So it's an array. Because of this, it's an array. ARR is an array with two elements of pointers, because of the star, right, to functions, because of this, whose arguments is int and which return int. All right, and you see that when we perform the initialization, the compiler doesn't complain. Okay. Now, why doesn't it complain? Well, f is actually a D function, right? But whenever we have something that is not 64 bits, all right, the compiler will try to implicitly convert it into something that has 64 bits, right? And the easiest thing to do is to convert it to the pointer to the address of that thing, right? So I could say here address of f and address of g, right? Remember this ampersand, which means the address of, right? So the address of an object gives me a pointer to that object, right? So this expression is a pointer to f. And then this also works, all right? But it so happens that this conversion happens implicitly. All right, so actually I don't need to put f and g inside. All right, so now let's do something with this array, right? For int I equals 0, I less than 2, I plus plus. We were very lazy and we wrote only two functions, and let's say printf for argument %d is %d backslash n, and then we're going to say I and array index I but this is not arg function %d, and we're going to apply this to 10. Okay, so this is the function, right? That we got from the array. And we further apply it to 10. Okay? So obviously we're expecting 11 and 12. Right, so now I can say func ptr, and I'm getting 11 and 12. Okay? So the important thing is that we can abstract functions pretty much in the same way we used to do it in Python using lambdas, right? It's a little bit more cumbersome, it's a little bit more clumsy, but the capability is there. Now, the real weird thing is the type of this array. How do I declare it to be an array of functions, right? So in Python it was very easy because we didn't have types, right? So here it's a bit more complicated. So again, this is an array. So from inside out, brackets bind tighter, right? So it's an array because of this, of pointers, because of the pointer, right, to functions that take an argument of int and return an int. Okay? So let's do something even more fun. Let's say I say something along the lines of int okay, okay, and I'm just going to do it like that. So int star star p, then what is p? So brackets always bind tighter, right? So p is a function, whose argument is int, that returns a pointer to a pointer to int. Okay? So if I were to, so in fact what happens is that I can't really declare such a variable, right? So function right? Because such a thing needs to have a body, right? So I can declare it here, but it's completely unusable, right? So what needs to happen is that I need to have an int star star p here. So remember how we were giving these declarations? We call them prototypes at the beginning of the program. So these prototypes I can put them anywhere in the program before the functions use it, right? So I can put such a declaration, and then later in the program I can say int x, and let's actually write a function that does that. So and let's put an n here. So we're going to return a pointer to a pointer of something. So we're going to say int star star result equals int star star malloc, just for fun. And let's say we use here an array 10 size of int star. Okay. So remember that between this guy and this guy, there should be one less star. Right? If you look at everything we've done, we've always done it that way, right? We had something like int star malloc 10 times size of int, right? So whatever is here loses a star always. So we could return this result, but it's not very usable, right? So what else do we need to do? We have 10 elements here, right? So this is an array of, it's a pointer to a pointer. It points to an array of pointers. Each of those pointers inside needs to be allocated. And you're going to say, oh, my mind is exploding. Does this really happen? Yes, it very much happens. it's in C, it's very much a thing. All right. So normally now we should do for int I equals 0, I less than 10, I plus plus, right? And I should say result I equals int star. So as soon as I put a bracket here, and by the way, when you see the bracket, and I've hidden the brackets away from you, this is the same as star result plus I, no difference, right? The brackets are a shortcut for this, and in general, the brackets are easier to write. So remember that it's not saving you anything, it's not in any way different, right? Result is a pointer, right? And we treat it as an array. So result is a pointer to pointer, right? So the elements are, remember we're reading from inside. So result is a pointer, so just one step. A pointer to a pointer to int. So we're reading from inside out, right? When I say a pointer to a pointer, I'm actually reading this star first. It's a pointer to a pointer to int. All right? So then, if result is a pointer to a pointer, result subscript I is going to be, this selection, okay, let me put a space here. So then, result subscript I is going to be this. So the bracket, remember, is equivalent of a star in front. So that star in front is this thing, which means that this expression's type is this, right? So let me make it even more obvious. Go back to this, right? So this star is this star, right? The plus I is just a subscript, meaning that the type is the remainder. The type of this is the remainder, right? So if I put the star in front, essentially I am matching this guy with this guy. So the type of this expression right here is whatever is left, which is a pointer to an int. So I have to allocate this. I have to allocate every single pointer in the array. I have 10 elements now. Each of them has to be individually allocated, right? So I will have an int star. So this is the type of this expression. So then malloc has to return an int star, right? Size of, and we could put another 10 here, but I'm going to be lazy and not really want to. So I'm just gonna say 1 star size of, and here is 1 star less, so we are going to have int, right? And now it would be nice to put something inside. So we have an int in there, right? So one thing we can say is star 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 plus I equals I, let's say. So now we have an array that is initialized. So in principle, it's safe to return this. Okay? Probably not working well. But what we have, again, result is a pointer to an array of 10 elements. Imagine it's 10 of them here. Each of them goes to another array of 1 element. And in each of these, we write 1, 2, 2, and so on. Right? So we're not writing in here. It's a double indirection. Right? I go from here, star, plus I, star, Okay? So, again, this is not something very useful, but let's nevertheless print it out. So for equals 0, I less than 10, I plus plus, right? So I'm gonna go here and actually go back to the nice syntax now that we've explained everything. Okay, so it looks like this. Yeah. Yeah, we start with that. Yes. Very good. And then printf. Well, elements. Let's percent d is percent d backslash n, and then we put I, and then star result I. Okay, so this should work. Result p, p, p. Uh, uh, not pi. All right, what we need to do um, is int star star x or r equals p of 10. So what would have been nice is actually, instead of saying I less than 10, to say I less than n here. All right, and then we can say r here. Okay, and that semicolon would be -2. And we're missing std lib. All right, so let's run it. And yeah, no big surprises. Okay, so what we did, this is the prototype for this function, right? Typically we write the prototype outside, but we don't have to. Then we call this function and we get a result of this type. Why? Because this is what the function says it's returning, right? And then because this r is a pointer to int, right? We can go through the array of pointers and get the first element. So you can think of this is an array of 10 elements of arrays, each of those arrays being of one element, because we allocated one because we were lazy. If I'd allocated more than one, I should have written another inner for loop inside here, right? So inside at this point, I should have written another for loop that would instantiate each of those elements. Okay, and I just was late. Let's try another example. Any questions so far? So let's do int, and this time I'm going to do star p 10 let's say char star. Okay, let's call it q, not p, q. So what's the type of q now? Again, the same rule applies from inside out, right? So q. So now I've put these brackets, which means that this star is tighter than these brackets, right? So Q is a pointer, right? Once I'm here, the brackets bind tighter than the star. So it's a pointer to an array of 10 elements of functions that return a pointer to int. Okay? Now, I don't want to write 10 functions, so I think we're just going to leave it there. But normally, we would need to initialize Q with something, right? So that becomes very interesting now, right? So if I need to say Q equals malloc, what do I write here? So yes, louder. Obviously not, right? If you look at what we did here, right? We had int star star, right? We had int star here. So it can be int, right? So the interesting thing is that you will just take this type. I'm going to copy it here. And I just delete the Q. And that's the type. So this is weird as hell. But it works, right? Now, sorry. Yes, yeah, that it is. That's what it is. Okay? So now the question is, what am I going to write in here? So I'm going to say 10 maybe times size of, and I have to put a type in here, right? So again, I'm going to take this type, I'm going to put it in here, and I have to delete a star, right? It's always one less star. Which star do I delete? The innermost always, right? So I'm going to delete the star. Okay? So this, yes, so what's wrong with that? Q declares an array of functions of time. Where is that wrong? Oh, I know. I cannot give it a size, I think. So definitely I can't give it a size here. But I think not even here can I give it a size. Is that I didn't save? Ah, here. Still, I don't know why it's wrong. It's a pointer to an array. Let's say if we remove this, does this work? If I use 2 pointers, does this work? Yeah, this would work. So I think it cannot be it cannot be a pointer to an array. It has to be an array of pointers. So I can never put the I can do this, but I can't do this. So if I leave it in this way, then I have Q is an array of pointer to, sorry, it's an array of functions that return pointer to int. So one interesting thing that we can do now is do this. And this should work. Let's do this. Let's comment this out and see. Still doesn't work. This definitive variable with array type needs an explicit size. So now I can say temp here. All right, so now it works. So I think I can't have a pointer to an array. I can have an array of pointers. That's the problem. So I can have an array of 10 elements. So an array of 10 elements of pointers. Pointers. This arrow here is a pointer, right? And then I'm at the bracket level of functions that take char star and return a pointer to int. All right. Now, if we try to do the malloc, okay, the interesting thing is I'm just going to delete this part. So I'm going to take this, Control C, and write it here, Control V. But this is an array now, so I don't need the allocation. This is an array. So I don't need the allocation. Okay, I should have tried to cook better examples. All right, let's try to cook a better example. So we're having a pointer to a function. A pointer to a function. That returns okay, forget about functions. Maybe all right, pointer to a function. that takes a char and returns a function that takes int and returns int star. Does this work? Function cannot return function type. Okay, forget it. I think I made my point already. All right, so these kind of things happen. How can we help this along? It can be helped along by defining types, right? So when we define types, for instance, if I want to define the type of a function that returns int, takes int and returns int, I can say type def int func type. Let's call it func type. Right? And then we can have something like func type star fh of func type star. All right, so we want to define a function and take in a function and return another function, right? How do we implement h? Can we implement h in a meaningful way, right? So notice that both f and g are have func type, right? So the type of f and the type of g are both func type. Okay. So let's say if we get f here, it's actually not a very easy way to return anything meaningful. But if I say, for instance, return func type x, so I can say return f. That should be a good definition. And then somewhere here, I could say printf some weird function. And we get %d. And then what we call is h applied to g applied to 100. And this should work, I think. Func type point func type. All right, so now if we run func pointer, right, it does what we're expecting to do, right? So what happens here? We have to provide an argument type here of this type, right? And G is such an argument, right? So definitely the type matches. And then we're returning F. Now you're going to say, why aren't we using X at all? Because we're lazy, right? And then HG, this value is F, right? So HG can be further applied to 100 and get a result. Okay. So yeah, so the types in C are a bit weird. right? But nevertheless, you can create any kind of chains of pointers that you want. It's a bit of an advanced topic. You might run into it. You will be prepared, and at least hopefully know where to look or know what to look for on the web when you see such weird expressions. Questions? Func type again? I don't quite understand the question. So, you see, I look at this definition, which you're familiar with, right? This one. So you have a type here and a type here, right? So I have a type here. Actually, this is the type. And a type here. Right? It's the same pattern. But looking at this definition here, right? Func type is the type of function that takes int and returns int. Right? So instead of having this weird syntax that we were trying to do previously with star and bracket, and we didn't know where to put the star and the bracket, and things didn't quite align, it's easier if we create our type hierarchy little by little by using type definitions. And then the interesting thing is that whenever you're doing a type definition, right? So this is like a declaration. This part is exactly like a general declaration, right? But if I put the type def in front, this guy becomes the type of what would have been otherwise declared, right? And this helps very much. So you can help your very complicated definitions, and you can make the pointers to pointers to pointers relatively palatable if you declare them incrementally. Okay? Okay. The other thing that I wanted to discuss today is library functions, and that's probably a more fun topic. So let's start a new file. So there's one area where the where C is extremely powerful, which is interaction with the operating system. Right? It has everything. Nothing is missing. It is the one language where nothing is missing in terms of controlling the operating system, to the level of controlling memory allocation policies and process priorities and so on. Things that you might not have in Python or even other higher level languages, right? Mainly because Python and Java try to be portable, meaning that the same program, when you move it across the operating systems, the expectation is that the program will behave pretty much the same, right? Now, C is not portable, meaning that my interface with the operating system on Linux or Mac OS is going to be completely different from what's going to be on Windows. Okay? You don't have the expectation of portability, but nevertheless, you do have the power. Now, I'm not going to dig into that because we don't have enough time and there's not enough knowledge about operating systems, right? But in general, everything that you know from Python is possible, just a bit more clumsy and a bit more cumbersome, right? You have already seen a few of the functions, so I'm going to add string to the page. Let's look at strings a little bit. Okay, so let's have two strings, which are star A equals A, B, C, C, D, F, G. So the one thing that you need to remember about strings is that there's always a \0 at the end. Whenever I write a constant, this is a constant string, there's always a \0 at the end. Okay? Char star b equals, let's use capitals this time. So let's do the first thing, print the length of one of them. We don't need both. And you already know that there's a function called stir_len of a, and that would give me the length. GCC minus O and that's very true. This should be an unsigned long. All right, and I get a length of 7. All right, let's try to do concatenation, which, if I remember correctly, we have a function called cat. Does this allocate? All right. So in the good tradition of C, this str cat is mutable. So what we're going to do is allocate an array of characters which we're going to use as a string. So I'm going to use a C, and I'm going to say size 20, right? And again, we're lazy. I should write a malloc and allocate exactly as much as exactly 14 characters, which is actually 15 characters, right? Because that's what we would need. So we're going to, in order to do a non-immutable operation, because we want to concatenate the strings, I'm going to copy the first string into C, and then I'm going to concatenate. So I'm going to do str cpy, and I will have to remember the arguments. All right, so destination comes first. So we're going to put C here and A here, right? And this should work fine. And then we're going to do str cat, and into C, at the end of C, we're going to put B. Okay? So then we're going to say printf concatenated %s \n, and we're going to put this string C. Right? So notice that C is an empty array of memory initially. This is initialized with random stuff, right? What we do is we first copy the A into C. This copy of A comes with the \0 at the end of A. So we see 7 characters, but actually there are 8 bytes. There's the 7 visible characters plus the 8th byte, which is \0, right? All these 8 bytes get copied into C. So C becomes a copy of A. And then we're doing the concatenation, meaning that we're going to have a pointer at the beginning of C. That pointer is going to advance 7 characters, and it's going to stop on the \0. And then it's at that position is going to start copying all the characters from B, advancing B until B reaches \0, right? And then that \0 is copied into C as well. So in the end, what we have is 15 bytes. 14 visible characters plus the \0. Okay, so let's see this working. Okay, and we see this. there's there are many other ones, right? So which I don't remember, so I could Google. For instance, let's try to find one that turns all the characters into upper characters. Now, the standard library of C is called libc, and it's the one that we're using right now. It's used by default. We don't have to put it in the command line, in the GCC command line. So libc uppercase, right? So we have 4 characters. We have 2 upper, 2 lower. But if I remember correctly, um, for string, uppercase, string. Oh, we have to write a loop. So there's no direct string. All right. So the good news is that we have a per character function that performs the conversion. Okay. So let's just do that for fun. Um, so we're going to take um, um, the characters in C and turn them into upper characters, right? So for char star P equals C star P not equal backslash 0 P plus plus, we're going to do that. We're going to do star P equals 2 upper star P, and then we're going to print percent s backslash n and C. Where does this come from? We had I thought it would be in string.h, but oh, ctype.h. There you go. So we have to say include ctype.h. Right, and we see that everything is uppercase. Now you're going to wonder you might be wondering, what are these files? All right, and they are just prototypes. They are typically found, let's see, in ASR include. No, I don't get ASR include. So I don't know where they are on Macs. But for instance, let's look at ctype. I think that's a smaller one. Ctype.h contents. C library. So let's see if we get that. This is not what I'm looking for. many years ago, I would get the first link I would get would be exactly the link that ctidal8 download. Can I do that? No, I can't do that. But this essentially, oh, I think this one. All right, so this is the file, right? So it looks like this, right? And when you see this kind of things, right, this is just a prototype, right? And the prototypes of the functions that we've been using, so for instance, we've been using, oh, none of these, right? 2 upper, 2 lower, right? Where's 2 upper? Not the one with an underscore. Oh, here, right? So we've been using this function, right? So it's just a declaration, right, which allows us, if we include this file is essentially pasted into our file. That's all that happens, right? And because of that, right, this prototype gets to be in the file. It declares the function, so we don't get the error of the function being used before being declared, right? So this is how it helps. We can create our own, and in general, it's a good practice to do that. So let's do just that for once. So I'm going to take this piece of code and I'm going to put it into a separate function, into a separate file. So let's call this function string to upper, str to upper. So we're going to say void str to upper char c. Actually, this should be here, right? And if we go to the other, so let's go incrementally, right? So instead of, so one thing that we can do now is delete these 2 lines, and we can say str to upper applied to C, right? And then, in the good tradition of what we have discussed previously, we say void str to upper char star, right? So this is essentially the prototype. And when I say that, when I write the prototype, the name of the argument here is optional. I can just leave it out, right? So now I have 2 files, okay? And then how do we compile the 2 files? Well, it's very simple, right? So I can say libs.c, and what did we call the other one? It's still untitled, right? We haven't saved it. Control S, and let's call it str to upper.c. And then I can just add to upper, and what happens is that this guy is no longer needed here, but it is needed here, right? It has to be in the same file where we're compiling, and it's the printf, so include stdio.h, right, and it works. So now, what really happens is, compilation under the hood has 2 phases, right? The compilation proper and the linking. And this is historical. Each of these files is individually converted into what we call an object file, right? then the two object files are linked together into an executable, right? So each file is processed individually without looking at the other one. This is something that used to happen because disk sizes were very small, and sometimes you would have to insert the disk with this file and get it compiled into an object file, then insert the file for the disk for this file. It was in the old days where, have you seen diskettes ever? At least in movies, Wikipedia. All right. It was a little square about this big. It had a disk inside. You would put it into a slot. You've seen CDs, right, and DVDs, right? Yeah. So the little box, because the magnetic disk was very sensitive, right? The little box contained a magnetic disk. It would go into a slot, and a little opening would just open and access the disk, and there was information there. And the size of a diskette, initially, the first one that came out was about 360 kilobytes. Okay, kilobytes. Now nothing is below gigabytes, right? Everything is gigabytes. So sometimes you would have to do these things, right? And it was important to be able to process these files separately. And that's why each file has to be sort of all the information that allows it to infer everything it needs to run. So for instance, this guy, right, it doesn't have the full definition, but it has enough information here to generate this invocation, right? And if you think of it, it kind of makes sense, right? That's all I need to generate the invocation of an unknown function. But at least I know what kind of parameters do I need to pass? Do I need to make any conversions? How do I use the result, right? It's sufficient. It's sort of like an interface. It's like a contract. Now, this thing, if this was a very widely used function, it's our own function, it becomes our own library, right? Then this might be very widely used. So then this prototype, I would have to include it everywhere. And it so happens that it's only one line, but my library might have 1,000 functions. So I might need 1,000 prototypes. So then what should we do? We should create our own H file. H stands for header, by the way. So I'm going to take this guy, I'm going to create a new file, and I'm going to call it command B, right? And I'm going to call it str2upper.h. We have created our own file. And then I'm going to say here, include str2upper. Okay. So at this point, this would still work, right? So this is just one line, whereas what I have here can be potentially 1,000 lines, right? Now, so this file has been included as if those declarations were here, and it still works. Notice the quotes as opposed to the angle brackets. So the quotes mean look in the current folder, right? Whereas the angle brackets say look into the system directory for header files, which is typically /usr/include on Unix systems, except for Mac. So I should be able to get these files from somewhere. I think if I search for 5 or 10 minutes, I will definitely find them. I don't want to be bothered, all right? But when GCC is installed on the system, it will have the notion of this is the system folder for the compiler, and in there will be libraries and there will be header files, right? And they're pulled from there. These are sort of standard. Okay. Now let's use a library that doesn't get passed in by default. So let's try to do some math. All right. Let's try to compute the sign of a value. All right. Yes. The names are not related. So the .h name and the .c name don't have to be related, right? So the name of the C file, you see it here, right? The name of the H file, you see it here, and that's the relationship, right? So here I have to use the correct H file, and here I have to use the correct C file. No, you never do that, right? H file are just pasted. It's like you're using copy and paste, right? And if you were using copy and paste, right? So delete this. So let's say I go and pull this file from the system directory, right? I delete this line, I paste the string.h from, get it from there, put it in an editor, copy from there, paste it in here, and it will work just fine, right? Obviously, it would create a mess of a source file, but it will work that fine, right? So these are very rudimentary tools. The system has evolved. Pasting is stupid. It's dumb, right? You don't want to work with pasting and with macros and the way C does. But at the time, the machine was not so powerful, and this was what was reasonable to automate. This was a reasonable way to automate. Okay, so let's try to compute, and I'm just going to add it here because it's just one line of code. So I'm just going to print sine of 1.5, right? So sinus is a function that works with doubles, right? Double values. So we're going to say print f, and sine of 1.5 equals percent LF, right? So it's a double. And we're going to say sine of 1.5 here. Now, if we try to compile this, we're going to get an error, right? So now it's so evolved that it's telling me that math.h is giving me a definition for this, right? So you would wonder now, why the heck doesn't it just run if it knows where to find it, right? But then it's a matter of backward compatibility, right? So you have to put it here, be backward compatible. So what happens if I do this now? Oh, it bloody works because I think the math functions are now implicit. So if I run this, I would get the value. Do you get the same thing? You shouldn't be getting the same thing. So are you able to compile? Let me see if I use clang. So there's another compiler. So let me try to use, maybe I get the correct behavior here. Oh, this one works too. So there are multiple libraries, right? The math library is the math library, right? So when you have libraries that are not passed in by default, you have to pass them in this form. So LM would be the math library. The standard library is LC, and we can pass it in even though it's not required, right? So you see we still don't get an error. Now, what happens? There's a standard folder, there's a standard directory for libraries, all right? And the math library would be called libm dot, and the suffix would be dependent on the system. So if you're on Linux, it would be SO. If you're on Windows, it would be DLL, right? But this is the name of the file. Now, this part, the lib part, and the suffix are always assumed. So what you have to put here is just, you remove those, and whatever is left you put here, right? There's the standard library that works for C is libc dot DLL or SO, or I don't even know what the Mac would use, right? So then if you say LC, right? The C here, the C that you see here, right, is the C that you see here, the lib and the termination arm, right? And there are many such libraries. For instance, there is a library for infinite precision arithmetic where you can use like um, um, numbers of infinite precision. Of course, those are not 64-bit numbers. They have their own proprietary encoding. So GMP would be, so the GNU multiple precision library, so you can pass it in, and then you see it doesn't find it, right? What do you do then? You go and download it from somewhere. So you're going to find somewhere lib gmp.so or DLL or whatever. You bring that binary here. You find the folder where all the libraries reside. You put it there, and then you say -lgmp, and you can use that library, right? So it's a very involved process, but that's how it works. If you don't want to put it in the system folder, or maybe you don't have the entitlements to put it there, you can put it in the current folder, and then you have to pass the -l, and you have to say that the current folder is also a library folder. So then it can look there, right? And then there are no libraries there, but it doesn't hurt to look, right? So then you don't get errors. So the interesting thing is that yeah, C has evolved quite a bit as I've been teaching this. I think most of the time libraries. So one way to install libraries, actually, I might need GMP at some point. Install GMP. Let's see if this works. So this could be a way to install a library. So while this is updating, it might not work actually. Let's go here and say no. Multiple precision library. So this is GMP. Format. Oh, it's the other one. So. Oh yeah, okay, so it should work. Still up there. But this is the command. Okay, so GMP, install GMP, and then if I pass -lgmp, then it will find a library and it will work, right? So this is another way of installing libraries. So libraries that are very well known, there will be a very straightforward way of installing them, right? There is a the environment that you're using will do it, right? Either on Mac or Linux, use the standard installation. In Cygwin, you need to pop up the setup again, and you need to look for this library in the menu options, and you need to check it, and then say run, and it will go and fetch it. Okay, it seems to be working. No, this is just the update. Sorry, it's not really working. Well, anyway. So this is pretty much what I wanted to talk about today, right? So in principle, everything that you were doing in Python is possible. It's a bit clumsier, but not really outside of reach, right? One important thing is that C programs are written in separate files, right? And most often than not, you write libraries rather than full programs, right? Nowadays, so you write a library that you load from Python, and then you write the top-level program you write in Python, right? You add some functionality that is not available in Python. That's a lot more common than actually writing a full program in C. Or you write plugins for for a browser, right? So they would be typically written in C, but it's not a main program. It's just a little plugin that performs a special task, and the full program is the browser. And then how do you access that plugin? Through JavaScript, right? So you load an HTML page, and you may have some new functionality, some new API that is available to the JavaScript that is running in your browser page. These are much more frequent projects that run exclusively. Use C from one end to the other, operating systems and compilers, right? But compilers also kind of C is losing ground. There are quite a few languages that are better. Haskell or Camel that are much better at writing compilers than C nowadays. Still, Java remains in C++, which is pretty much a slightly enhanced C, and Python is written in C. At least the virtual machine is written in C. Questions? But you see, the first thing that's available. Let's say you're bootstrapping an operating system. You want to write a completely new operating system, right? So you have a new computer system, right? The only thing that's available to you is assembly language. One interesting thing that I should have shown to you, and I might still be able to show, is a little bit of assembly language. So let's take the program that we have, this file that we have just written. How was it called? str to upper. So gcc -c -s str to upper. You don't need to take this down. And okay, so cat. I've never seen assembly language files for the Mac. This was going to be a first for me. Okay, so this is a language which some people actually coded. I used to code in this. All right, so each of these mnemonics tells the processor to do something very simple. For instance, move data. This is a register, and this is another register, but we're using this register to point to an address, right? So from register RDI, we're transferring to the memory address pointing by this guy, -8. -8 being 64 bits, so it's actually it's star p. This is a star p -1, essentially, right? So you see the code that we've written was two lines. Remember the str. So we have here like what, 30 lines of assembly language, right? When you have a completely new system, what you have is essentially assembly language for that computer system. This is what you have to start coding in, right? Now, one relatively easy thing to do is a cross compiler. So I have a compiler that runs on my Mac, but generates code for that new system. And I'm going to put a cable between this computer and that board containing the new processor, and I'm going to take this, convert it to assembly language, put it here, and see this running, right? And this maybe will have a few LEDs, maybe it will have an LCD, some sort of a screen, and I'm going to run code, and I'm going to slowly develop this system and develop an operating system for it, right? At some point, I'm going to take the compiler, let the compiler compile itself for this guy. And at that point, I have a way of writing high-level code for this guy, right? So these are the steps of bootstrapping a machine, right? Then I'm going to develop an operating system for this guy with the compiler that I have just bootstrapped. Once I have an operating system, I can think of Python and other things, right? So C at that level, when it's the system is just emerging, it's the most instrumental tool that you have. All right. And then this is how C worked in the beginning, was a portable assembly language, right? was you were able to take the same instructions, right, but not the same libraries, right, but the same instructions, and generate code for, say, 8086, and generate code for Motorola 68000, and generate code for Z1, Z10, IBM Z10, and so on, right? So these were just different systems with different processors at the time. And you would have Unix on all. So that was the big breakthrough that happened somewhere in the 70s. Yeah. And it was a big breakthrough because you could write one operating system, which was 90% written in C, that was Unix. And then that 90%, you could add the 10% that was specific to the system and written in the assembly language of that system. So assembly languages are different across different machines, right? And then bootstrap a Unix for each machine, so 10 times faster, right? Because the 90% that was written in C was always, didn't have to be rewritten. That was the big breakthrough at the time. Now, of course, it's nobody writes really open writes operating systems anymore. There's 3 of them, and the world has stopped there essentially, right? They are maintained, but each of them has a life of its own, has all the tools that you need. So nowadays, it's very you don't get to that level unless you're a hobbyist, right? You buy a Raspberry Pi, you know, those Raspberry Pi, Arduino, right? And then, right? And what are you coding in? Do you have a Pi or an Arduino? Yeah, for Arduino you have to be coding in C, right? Yeah, so for Arduino, you're doing exactly what I was saying. You're cross-compiling, right? You have a tool that runs on your Mac, but sends the code to the Arduino. Compiles locally, but compiles for the assembly language of the Arduino and sends the code over to it via USB. So for a computer engineer, C is a very an essential tool, right? But